All right, so this leads us, the previous topic leads us to a general Poisson approximation theorem. Which is good to be aware of it. There's a whole theory of Poisson approximation, much beyond what we'll talk about in this course, of where the Poisson distribution can be used to approximate the distribution of other random variables. So here's just a taste of what that might look like. So for each n, we're going to assume that we have a collection of n not necessarily independent, and not necessarily equiprobable. So they just don't have to have the same probability of happening. They don't have to be independent. But we have n events. And we're going to define capital N sub little n to be the indicator for these n events for each n. So it's the number of events that occur for each n. Then if n, we think about if n goes to infinity and if the AI n's vary with n, so that this quantity S sub kn, which we have defined before, but now it varies with n. It's the sum over all size k subsets of the probability of the intersection of the aijn. Such that this converges to some value lambda to the k over k factorial for each k. Or some value of lambda. Then the distribution, the probability that nn equals j for each j, converges to e to the minus lambda to the j over j factorial for all non-negative values of j. So in other words, this random variable that we defined here converges, can be approximated for large values of n by the Poisson distribution. And so the intuition for this is that in general, if we have a large number of things, of events, each event has a small probability and they are approximately independent. Then n sub n is approximately Poisson. So that's a pretty general way and a pretty good way to understand and to think about how the Poisson distribution comes up and why the Poisson distribution is so common in a lot of applications involving count data.